Interesting, interesting. Huh, who knew? All right. Hey guys, it is 4:55 on a Saturday, which means it's time for a little econometrics. I forgot to plug in my higher quality camera today, but that's all right because today's mostly going to be on slides. All right, so today we're going to be talking about difference in differences. The slides for these are up on Moodle. This was actually converted from the lecture that I used to get a job at Occidental. When I applied for a job here, they had every candidate give an example econometrics lecture, and they asked me to talk about difference in difference. So then I slid it right in to 272. So uh, difference in difference is the one topic that we cover in this class that is not really covered in the textbook. So this lecture, the worksheet, and the slides are kind of your main resource for difference and differences going forward, and let's just go ahead and dive into it. So I'm going to teach you about difference and differences kind of using one example. Difference and differences is a regression technique. It's not an OLS violation like we've been covering a lot after the first midterm, and it's not actually its own. Well, it is its own type of regression, but it's really just a specific type of regression rather than something that could go wrong with a regression or something that you need to do differently. So difference in difference is an incredibly popular kind of regression technique for analyzing public policy. And so we're going to use that as our running example throughout class today, or throughout this lecture. So you could imagine that a few years back, the Los Angeles Unified School District was considering a $7 billion bond measure to improve school facilities. They actually just recently, I think on this upcoming ballot, are having a similar bond measure. And so you might ask yourself, if you're a policymaker, should we be spending $7 billion on improving our schools? And so, of course, having better schools that have better air quality, more green space outside, better lighting in the classrooms, in an ideal world, we'd have all of these things, but is this the best use of $7 billion? If even if you say we want to spend this $7 billion on students or on education, is improving facilities really the right way to go? To understand that, you need some kind of causal evidence on the impact of improving school infrastructure. And so let's kind of think about how you might go about finding that sort of causal evidence. The first thing you could do is you could collect data on a lot of different schools. There's actually, if you go to the National Education Statistics website, you could look up your own school district, wherever you went to school, kind of find these data for yourself. And so let's say that the outcome you wanted to improve was maybe literacy in schools. So for this example, we're gonna be thinking about, when I say students, let's be thinking about kind of elementary school students, maybe third, fourth, fifth graders. And so generally speaking, if you're improving school infrastructure, what you're doing is you're spending more on that school. In particular, you're spending on the building, but you're kind of spending more on the students through infrastructure. So you could run a regression where your outcome variable is literacy, maybe the literacy rate at a school or in a school district, and your independent variable is spending in that school district. Think to yourself real quickly, or hit pause on the video, to ask yourself, why might this regression be causal, or why might it not be causal? Just to give you a sense of kind of what the data look like in the US. I have a few school districts here, including Oakland Unified, where I did my public elementary school, and it also includes down at the bottom Winchester School District in Connecticut, which is the most highly funded school district in the United States. And so you can see that in different school districts around the country, spending is widely different on a per student basis. So in Oakland, students, on average, the government spends about $11,800 per student per school year, whereas in Winchester and Connecticut, it's $38,000. Somewhere like Riverside, it's only $9,500. And so you could imagine that the spending rate correlates then with the literacy or the illiteracy rate, as it may be, in these different school districts. So if you ran just this regression, kind of um, using these data, you could collect this for all the school districts in California or something like that as your outcome variable using literacy as your explanatory variable. You would get a coefficient, and that would tell you maybe for a $1,000 increase in, or sorry, did I switch that up? Literacy is the outcome, spending is the independent variable. And so beta 1 would tell you for maybe a $1 increase in school spending or a $1,000 increase in school spending, how much could you expect the literacy rate to go up by? If you ran that regression, there would probably be a lot of omitted variables bias. Why is that? Well, the sorts of school districts who tend to spend more money on their students are probably also very different on other dimensions. So school districts that spend more money typically might have wealthier families living there. So maybe the correlation might not be the actual spending on the students. It's that students who come from families with more resources have better outcomes when measured by things like literacy. Maybe it's that there's better teachers in the places with more school spending, or that they have smaller class sizes, or that the crime rates are lower, and so students have more ability to focus on school. Maybe you could control for those things in your model, but then there's also, I guarantee you, going to be other things that are correlated with school spending, like the quality of the principal or the determination of the students, that will be really hard to measure quantifiably. So just saying like, oh, let's just add in some more control variables, you're never going to get totally around omitted variables bias in this case. Another approach you might take might be to kind of think about time series data. Let's look at one school district over time and say to ourselves, how has the literacy rate in that school district changed as we have changed school spending in that school district? So the nice thing about just looking at one school district and following it over time is that you're kind of holding constant all of those things from the previous slide that I say vary across school districts. If we're looking at just one district over time, well, the families that are living in that neighborhood are the same, roughly the same over that period of time. The class size is going to be roughly the same. Things like crime rate and teacher quality, they might be changing a little bit, but those things change very slowly. If you have a sample of 10 years or 20 years, you're essentially holding constant all those things if you just focus on one school district. However, there's going to be a problem that there are other things that are changing over time that might be correlated with school spending. So maybe spending is higher in years that there is a better economy. That might mean that the coefficient you estimate on school spending, beta 1, might not actually be due to the fact that spending on the school, that is increasing the school's budget, is causing literacy to go up. It might be that in years where spending is higher, it's also the case that families tend to have a little more money in that year, and so maybe they're able to feed their students with better nutrition, or there's just less stress in the household, or whatever it may be. And so again, we don't have a causal relationship, it's just a correlational one. So sort of two big picture approaches that we could take to trying to understand the impact of school spending on literacy, one being cross-sectional data, where we compare lots of different school districts in the same year. The other one being time series data, where we look at the same school district over many years. Both of those fall prey to omitted variables bias. A solution that we're going to see, the point of today's lecture, is what's called difference in differences. Difference in difference is a special form of regression. It uses interaction variables, which we first talked about in the functional form lecture, and it's great for public policy analysis, because public policy type issues often kind of fall into the requirements for difference in difference. To run a difference in difference model, you need two things. First of all, you need data from at least two time periods, what we're going to call pre and post data. Pre is going to be before some intervention, and post is going to be after some intervention. And then you also require observations on some units, some observations in your data set that are treated, and others that are unaffected or control observations. And what difference in difference does is it compares the relative changes of the control group to the treatment group over time to get a causal estimate of the impact of the variable of interest. And as we'll see at the end of the lecture, it's able to avoid many of the omitted variable bias issues. So the example we're going to use is that we're going to go back in time to, I think, the early 1900s, and this program called the Rosenwald Schools. So Mr. Rosenwald, you can kind of imagine the Monopoly man, some wealthy old man with a top hat and a white mustache. And he was appalled at the quality of public schools, especially for non-white students in the rural South. And so he decided to create a program to build 5,000 schoolhouses through matching grants. So a school district could apply for a $1,000 grant, and so long as the school district themselves were willing to put up $1,000, Rosenwald would match it, and so essentially double their money. Some counties got multiple schools built, some counties got no schools built. So the map that you have here is a map of the number of schoolhouses in a school district that were serving non-white students in early 1900s, and this was before the Rosenwald program. And then on the right is a map of the number of schoolhouses in a school district serving non-white students after the Rosenwald program. So you see that afterwards there are still white or counties that don't have any color. So these are counties that still don't have any non-white schoolhouses, but there are so many more than there were before. In a nutshell, we're going to get into the actual implementation using a regression in a second, but in a nutshell, what we're going to do in a difference in difference is sort of compare how did the counties who did have schools built fare relative to the counties who did not have schools built. Probably, kind of going into it, counties, maybe in this part of Tennessee and counties in this part of Tennessee might not have been all that different, or counties who were just over here in Mississippi versus counties who were just across the way here in Alabama are probably pretty comparable in terms of they're close in proximity, probably pretty comparable in terms of family background, the sorts of people who are living there, and sort of these other omitted variables we might be worried about. And so it's going to make for a nice what's called natural experiment. Oh my goodness. Someone hijacked my slides and put in a bunch of pictures of just an incredibly cute young child. I have no idea how that happened. This is very unprofessional, and I apologize deeply. Okay, so how do you implement a difference in difference regression? A difference in difference regression always takes the same form, and that is there are the first kind of three control variables are always the same. And they're all dummy variables. So there's the first dummy variable is going to be a dummy variable called treat or treatment, and this is going to be a dummy variable equal to 1 if the observation was ever treated. The second variable is going to be called post. This is a dummy variable indicating a point in time. So whether a certain observation is after the treatment has taken place or not. And then the third and last dummy variable, and the one that's going to end up giving us our causal estimate, is going to be called, is the interaction between treatment and post. So those two variables multiplied together. In this Rosenwald example, for every county in the South, there are going to be 2 observations. So if we think about in Alabama, Bibb County, let's imagine that Bibb County is a county that did have a Rosenwald school built in it. Rosenwald in this table is akin to treatment. So having a Rosenwald school built is our treatment in this case. Okay, so Bibb County did have Rosenwald schools built. So for both observations of Bibb County, the Rosenwald variable is equal to 1. All right, and for Bibb County, only the second observation, which maybe the second observation is measured like 10 years after the school was built, has post equal to 1, because post is indicating whether this kind of observation occurred after the Rosenwald schools were built or before. And then for both cases, we have the literacy rate over here. So in Bibb County, the literacy rate went up by 9% before to after the Rosenwald schools were built. And then the interaction variable is equal to post multiplied by Rosenwald. So the first one is equal to 0 because post is equal to 0. The second one is equal to 1 because post and Rosenwald are both equal to 1. In a county like Auburn County, let's say Auburn County never had a Rosenwald school built, so both values of Rosenwald are the same. for any county, their Rosenwald value is going to be the same for both observations. And for every county, their post value is going to be 0 beforehand and 1 afterwards. And so because Rosenwald is equal to 0 in both cases, for Auburn County, both of their post times Rosenwald is equal to 0, because 0 times 0 is 0, and 1 times 0 is 0. And then you can go and you can do the same thing for Boonville County and for every county in the rural South. Doesn't mean the literacy rate isn't changing in these places, even if they didn't have Rosenwald schools built, but maybe it's not changing by as much, maybe it's changing by more, who knows? That's kind of what the goal of the study is to find out. Here is kind of a visualization of the difference in difference. Orange dots are your control districts, green dots are your treatment districts, and time is on the x-axis, and so the literacy rate is on the y-axis, and so what we have is sort of a lot of schools beforehand, and then those same school districts afterwards, with an overall kind of change in literacy. These are kind of how, if you were to graph the dots from the table, this is what it would look like. Ultimately, you can visualize a difference in difference rather than considering kind of every dot individually or every school district individually. We can kind of think of the average of these different groups. So the first two averages we can consider are going to be called y bar t0 and y bar c0. Y bar t0 is going to be, so y bar is going to be the average literacy rate, y bar being the average. T is going to reference treatment groups, and 0 is going to index, our subscript here is going to index time. So y bar t0 is going to represent the average literacy rates in school districts that would eventually have Rosenwald schools built, but haven't had them built yet, because we're talking about beforehand, time 0, but schools that are going to have Rosenwald schools built, whereas y bar c0 is going to be the average literacy rate before any Rosenwald schools were built anywhere in counties that are not going to have Rosenwald schools built. And then we have y bar t1. That's going to be the average literacy rate in counties that did have Rosenwald schools built afterwards, and y bar c1, which is the average literacy rate in counties that did not have Rosenwald schools built after they had been built in other counties. And this table that I'm building here, I want you kind of by the end of this lecture, you should have a good command of how this table works and how it connects back to the underlying regression. Okay? So you can imagine looking at the difference between the treatment and the control counties before any Rosenwald schools were built. That's going to be the vertical bar here on the left. And then you can imagine looking at the difference between those counties after the schools were built. That's going to be the vertical bar here, or the vertical distance here on the right. And what a difference in difference does, what this regression is doing, is essentially estimating the change in the gap between treatment and control. So the cool thing about difference in difference, before I kind of go on, is you'll notice that the controls, what we're calling the control schools and what we're calling the treatment schools, do not start out in the exact same place. Normally, if you're using the language of an experiment, like a randomized controlled trial, like maybe you're trialing a new drug and giving some people a placebo and some people the real drug, you want your treatment and your control groups to be identical beforehand. That would be great, that would be ideal, but it might not be feasible when you're kind of dealing with real world data. Oftentimes, real public policies don't get implemented on a randomized basis. They get implemented by, not that it's non-random, but they kind of get implemented where they get implemented. There's an entrepreneurial government agent somewhere, or someone works hard in one district and not in the other to get this thing implemented. The nice thing about difference in differences is it's going to be okay if the control group and the treatment group are not the exact same ex ante, if they're not the exact same before the treatment takes place. So in other words, it's okay if when we go all the way back to our map of these school districts, when we go back to the map, it's okay if sort of the school districts that eventually are going to have Rosenwald schools built. So it looks like kind of, low eastern uh, Tennessee is going to have a lot of these schools built, whereas upper middle Tennessee is going to have fewer of them built. It's okay if these two groups of school districts are a little different even before the Rosenwald schools were built. In other words, it's okay if there's going to be some omitted variables that aren't in our model that might be a little different between these two places. And that's going to be a big part of the key to difference in differences, is that it's okay if there's some initial differences between the two. All right. So ultimately, a difference in difference estimation is going to be the change in the gap between this vertical distance and this vertical distance. And that's represented on this next slide. That this full distance here was the difference in literacy rates between control and treatment schools before any Rosenwald schools were built. This smaller vertical bar here is the difference after they were built. And so what we're going to say in this case is that the causal impact of the Rosenwald schools, the difference that the Rosenwald schools made in terms of literacy rates for non-white students in the South, is this third vertical bar, kind of the difference between the two differences, hence the name. By this point in the lecture, you're probably all sick of me saying the word difference. This is just kind of a simplified version of the graph representing it with lines rather than dots, but as you can see, kind of the treatment line, the green line towards the bottom, is a little steeper than the control line, and so this is representative of catching up. The dotted green line is the same slope as the orange control line. The dotted green line in this case is sort of thought of as the counterfactual. That is, we believe that had Rosenwald not come in and built these schools, that the treatment districts, the places that did get the schools built, would have sort of been on the same trend or the same path as the control schools. And hence, the difference between this counterfactual line and where the treatment schools actually ended up, that is what we can attribute to the impact of the Rosenwald schools, or in this case, kind of what we can attribute to the impact of greater school spending on student achievement. You could also think about difference in differences in a second fashion, and that is, rather than thinking about it as the difference in difference between before and after, you could think about it as the differences in gains. So y bar t1 minus y bar t0 is the change in literacy rates for treated schools before and after Rosenwald schools were built. Y bar c1 minus y bar c0 is the change in treatment in literacy rates for control schools before and after Rosenwald schools were built in other districts. No Rosenwald schools were built in control places. And if you subtract one of those from the other, you get the exact same formula as you did if you did the differences using kind of the differences before and the differences afterwards. Okay? So difference in difference can be thought about as the differences in two different ways itself. Either the changes in treatment minus the changes in control, or the changes beforehand minus the changes afterwards. Or the changes afterwards minus the changes beforehand, rather. Now we connect the dots between using just means of the outcome to what a regression is doing. This regression equation has kind of been hanging out here this whole time, and so now we're going to connect the dots between those two. So in a regression, what is the intercept? The intercept represents the average outcome value when all the explanatory variables are equal to 0. So when are all the explanatory variables going to be equal to 0? Well, if all the explanatory variables are 0, that means we're talking about a county that is not treated, so treat is equal to 0, and we're talking about that county before Rosenwald schools were built, so that post is equal to 0. And if treat and post are both equal to 0, then the interaction term is also going to be equal to 0. So the intercept term in this case is representative of the average literacy rate in control counties before Rosenwald schools were built elsewhere. In other words, y bar C0 can be thought of as beta 0. We can draw a direct comparison between the box on the previous slide to this slide. The average literacy rates of treatment schools beforehand, before Rosenwald schools were built, can be thought of as beta 0 plus beta 1. The constant term, beta 0, applies to everyone. That's kind of the intercept that gets applied to all observations. For treated schools before any Rosenwald schools were built, their value of treat is going to be equal to 1. So the value of beta 1 is going to get kind of applied to those schools, or that's part of their predicted value. However, this is before Rosenwald schools were built, so their value of post is equal to 0, and thus their value of the interaction term is equal to 0, because it's treated is equal to 1 multiplied by post, which is equal to 0. Bibb County in Alabama, beforehand, can be thought of in this way. So in other words, this box, the treatment pre-box, can be thought of as the average of all counties like Bibb County. Counties that were measuring before any Rosenwald schools were built, but that will eventually have Rosenwald schools built in them. The difference between counties before and counties, between treatment counties before any Rosenwald schools were built and control counties before any Rosenwald schools were built is thus beta 1, because you have beta 0 plus beta 1 minus beta 0. Go over to the graph. If you run this regression above, what beta 1 is going to represent is the difference in literacy rates between treatment and control counties before Rosenwald schools were built. All right, now we're going to look at the same thing afterwards. What is the average value, average literacy for control schools after Rosenwald schools were built? It's going to be beta 0 plus beta 2. Again, this might be, so like Auburn County afterwards, kind of think of it as the average of observations like this one, where post is equal to 1, because we're now talking about after the Rosenwald schools were built elsewhere. The intercept applies to everyone, but the interaction term is going to be equal to 0, because these are counties that were never treated. So beta 0 plus beta 2. For treated counties after Rosenwald schools were built, all four coefficients, beta 0, beta 1, beta 2, and beta 3, apply to them, because beta 0 applies to everyone. These are treated counties after the Rosenwald schools were built, and thus 1 times 1 equals 1. So this is this kind of last box you can think of as like Bibb County there. The difference between these two columns, between beta between the treatment and control afterwards, is beta 1 plus beta 3, right? Because beta 0 and beta 2 apply to both of them, so the difference between these two is beta 1 plus beta 3. And thus our difference in difference, which is representative of the exact same thing that we were talking about when we were talking about it as a difference in means, the difference in difference can be completely described just as the coefficient beta 3. In other words, the coefficient on the interaction term represents the relative gain or loss that treated observations made relative to control observations before and after the experiment. So beta 2, so looking at it on the graph, beta 0 is the overall intercept. It's where control schools started out beforehand. Beta 1 represents the difference between control and treated schools beforehand. Beta 2 represents the difference between control and treated school districts afterwards. And beta 3 represents the difference between that counterfactual gain for treatment schools and where they actually ended up. In other words, beta 3 represents the difference in difference, the relative gain of treatment schools over control schools. So this is pretty nifty because just using 3 dummy variables, a pretty simple regression setup, you can then estimate this sort of complicated relative gain model. And as opposed to just using the comparison of sample means, like we did in the earlier part of the lecture, The benefit of doing this through a regression is you still get to find out things like statistical significance. If you just compare sample means, you don't actually know whether the difference in difference that you find is statistically significant or not. If you do it using a regression, then the regression is going to calculate the standard errors. It's going to understand whether or not this is a finding that would have arisen by chance or not. The other advantage of doing this using a regression format is that in a difference in difference model, you can also control for other control variables if you wanted to. So maybe you could add in a control for the percentage of the state population that is Black or African American. You could add in a control variable for the average family income in a school district. You can sort of add in these other control variables that might help better explain the outcome, that might make your adjusted R-squared go up, while still uncovering the true kind of causal impact of the coefficient of interest. So in this case, of the kind of building of these Rosenwald schools. For those that are interested, this kind of example didn't come out of nowhere. This came from a real research paper that was published, maybe 15 or 20 years ago, where some economists went back to look at historical data of this Rosenwald program, kind of mapped, used the census to kind of understand demographics of these different counties and estimated the impact. And what they found was, sure enough, so here we have, they used gamma rather than beta as their coefficients, but gamma 0, this was the kind of intercept of literacy rates. Gamma 1, this was the difference beforehand between the two schools. So treatment schools had about a 5% higher literacy rate beforehand, holding the other variables in the model constant. This was the difference between the two afterwards. And 0.064, this was the difference in difference. So 0.064 is representative of, and this is different from, I should note that the graph that I made kind of in my slides is not to scale or not representative of this true experiment. But the interpretation, what the authors found, was that the Rosenwald schools made a 6% percentage point gain in literacy rates for school districts that did build these rather than for ones that did not. When the authors add in all of the other control variables, so this first model is just using the 3 coefficients. This second model, this is from the same regression, but where they add in lots of controls like for income and race and political demographics and stuff like that, and the overall coefficient does not change by very much. So it's a pretty robust finding. So kind of going back to the initial motivating example, if you're a policymaker who's trying to consider what is the benefit of spending a lot of money on school infrastructure, you might go look to the past. In this case, we went all the way back to the early 1900s. You could go look at more recent cases of this as well, but you look to the past and you do a sort of causal analysis to try to understand, well, in the past, when people have spent money improving the infrastructure of schools, has that actually made a difference to student outcomes? That'll then help you kind of understand the cost and benefits of the program that you're proposing. So to recap, what is difference in differences? It's one of the most commonly used analysis tools in social science research. It's not strictly used in economics. It's used in sociology, psychology, all the time, political science. It uses this idea of natural experiments, of kind of trying to find observations that are or sort of similar, or kind of any one of them could have been treated, just only some of them were. And when it's used correctly, it can provide causal estimates. Not every data set is applicable for difference in differences. For a data set to be applicable, you need 2 things. A treatment variable, so which means you need treatment observations, some observations that got something, other observations that didn't, and you need before and after data. How does difference in differences overcome omitted variables bias? It's a little subtle to see, but we'll talk about it right now. Our normal formula for omitted variables bias is that omitted variables bias is beta k times alpha 1, or maybe that should be alpha 1 hat. I'll go ahead and put a hat on it, because that's the way we normally talk about it in class. And so if we're thinking about the Rosenwald schools example, where maybe an omitted variable is family income in the school district. So you might be worried that school districts with wealthier families inherently spend more money on those children. And so what you might be picking up is not the impact of the actual increase in school spending. It's just that places that tend to have more family income tend to spend more on the students. Okay, so the amount of bias caused by an omitted variable is the product of beta k, which is what is the impact in this case of family spending on literacy if it were included in the model, and alpha 1 hat, which is the correlation between the omitted variable, family income, and the coefficient or the variable that is included in the model. The neat thing about difference in difference is the causal variable is the interaction variable, treatment times post. And because it's the product of two variables, for alpha 1 hat to not equal 0, it has to be a variable that is correlated with both treatment and post. And it turns out that most variables are not going to do that. So omitted variables that are correlated with treatment, correlated with whether or not schools got Rosenwald schools built. So maybe school districts with better teacher quality or higher family income were the school districts that got Rosenwald schools built. These are examples of variables of things that might be different across different school districts. They might be correlated with treatment, but they're not correlated with post. In other words, these things are probably true both before and after the Rosenwald schools were built. And then we have omitted variables that we might be worried about that are kind of changing over time, like trends in the economy, trends in parenting styles. So like maybe over this period of time, it was becoming more popular for parents to start reading to their children. And so the literacy rates would have gone up even without the Rosenwald schools. So that's true. These are both omitted variables, but these things that are correlated with time, they might be correlated with the post variable. In other words, after the Rosenwald schools were built, maybe the economy was better, maybe parents read to their children more, but these overall national trends are not going to be correlated with treatment. They're not going to be correlated with the specific school districts that did or did not get the Rosenwald schools built. So yes, there are a lot of omitted variables, but by using the interaction term, the correlation between the omitted variables and the interaction term is going to be 0, because most variables are only correlated either with treatment or with post, and thus the omitted variable's bias for beta 3 for the coefficient on the interaction term, going back to beta 3, the omitted variable bias on beta 3 is going to be 0, because the variables that are omitted from the model might have non-zero beta hat k or beta k's, but they're going to have essentially 0 alpha 1 hats, because the correlation between these omitted variables and the interaction term is going to be 0, because almost no variable is correlated with both these things. It's only correlated with one or the other. And so lastly, as a note on difference in differences, there is this is just the convention. You could, if you wanted to, define your dummy variable as 1 if an observation was control and 0 if it was treated, or 1 is pre and 0 is post. But it's convention that treatment is equal to 1, post is equal to 1, control is 0, pre is 0. And it's also convention that beta 1 is the coefficient for the treatment dummy, beta 2 is the coefficient for the post dummy, and beta 3 is the interaction term, the treatment times post variable. Difference in differences have been used in all sorts of public policy settings. It's been used to study the impacts of the minimum wage, looking at some states that raised their minimum wage compared to other states that didn't. It's used to measure school attendance in India, the impact of cigarette taxes, the impact of hosting major sporting events like the Olympics or the World Cup. So you compare the cities that ended up hosting the Olympics to the cities that didn't, that bid for the Olympics or bid for the World Cup but didn't get it, and you assume that they are kind of relatively comparable. Things like air quality, so it's used in environmental economics, health economics, macroeconomics, microeconomics, kind of all over the place. It's a really cool technique to know. And the last thing to kind of know about difference in difference, and we're not going too far into it, is that the assumption that it makes is that the treatment and control groups were on relatively similar trends before the intervention took place. In other words, you are sort of assuming that your control group is a decent counterfactual for the treatment group. But if that assumption is true, and that assumption only is true, then you have a causal estimate of the impact of the treatment variable without having to worry about omitted variables bias, which plagues so many other kind of cross-sectional regressions that we do. All right, so that's it on difference and differences. We're going to be doing a worksheet on it later on in the course. For some of you, on your final projects, I might mention that difference and differences is applicable to you. That doesn't mean you've chosen a good final project or a bad final project if I do or don't say it. Just sometimes the difference in difference is an appropriate regression to be running. Again, it's going to be for students who kind of naturally picked a topic that has both a before and an after component to it, rather than a cross-sectional or a single time series component. But so if you see that in our feedback conversations that we have, now you know what it is. And if you want to go ahead and estimate one in your final projects, that would be great. Not a requirement, but something that I think would be a rewarding kind of thing to attempt. So hope everyone is staying healthy, staying socially distant, and I'll talk to you guys very soon.